Welcome student to part 2 of the potential and conservative functions. In this example, I have a vector field consists of a 3-component ijk, and the first question I need to find whether this vector field is conservative. Now, remember, one way to find if a vector field is conservative is to calculate the curl of f, which is the gradient cross f. If this is 0, then whatever I have is a conservative vector field. So this would be I, j, k, and then we do partial by partial x, partial by partial y, partial by partial z, and down here we write the components that we have. So it would be sine y, x cosine y minus cosine z, and finally y sine z. And we find the curl here. So in order to find the component of I have to do this derivative. This is sine z. So I'll just write sine z minus the component of this one. Again, it will be sine zi. So this is 0 minus, now for the j, it would be already 0. And for the k, it would be just cosine y minus cosine y, which is again equal to 0. So it is conservative. Question number 2, part B, we need to find a potential function that work for this one. So in order to find a potential function, remember a potential function is a function where the gradient is equal exactly f. Now this means if x is the first component, if y is the second component, if z is the third component. So we have sine y I plus x cosine y minus cosine z j plus y sine zk. So in order we have fx equal sine y, this is the first equation, fy equal x cosine y minus cosine z, and finally if z equal y sine z. Now of course we can start with any equation that we like, but I think the most informative equation is the third one. So what I will do, I will find the integration for this one. So I will get f of x y z, so I will integrate it with respect to y because it has more components, and that integration will be x sine y minus y cosine z, and because there is a 2 constant, so I will write it as c of x comma z. Now all what we need to do is to find this constant. So what I will do, I will substitute in the first equation. So back to the first equation. If we go to the first equation, we find the derivative with respect to x. We get sine y plus cx x comma z equal to sine y, which means cx equal to 0. That means c of x comma z is actually only a function in z. It has no x at all, and that's why the derivative is equal to 0. Now substitute finally in the third equation. And that's what we will get. If we substitute in the third equation and we find the derivative with respect to z, we will get minus, or we get just y sine z plus c prime equal y sine z. So again, that means c of z equal just a constant. So in short, what we get is exactly this one plus a constant. Now, in the third one, we need to evaluate this integral over this curve. Of course, here we can just find what we found before, that f is exactly this one plus a constant. So here all what we need to do, we apply the fundamental theorem of line integral so we get the integral cf dot dr equal, we take our f and we substitute r of 2 pi, the endpoint, minus we take f and we substitute r equal to 0, which is the start point. So this is equal to f. If we substitute 2 pi, what we will get is 0, 2 pi, 4 pi, minus f r of 0, this is just 0, 0, 0. Now if we substitute those in the function itself, what we get is this will be 0 minus y, which is 2 pi cosine 4 pi, plus c, minus, if we substitute 0, of course everything will be just c. So the final answer will get to negative 2 pi. Thank you for watching.